Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on area and volume scale factors. So we're going to look at what happens to the area or volume of a shape when we enlarge it and make a similar shape. So let's look at these rectangles on the screen. So let's say this first rectangle is 5 centimeters by 2 centimeters, and no surprise, its area is just 5 times 2, 10 centimeters squared. So let's look at the one to its right. So let's double the length of each side. So what will happen to the area? Will its area also double? Well, this side would become 10 centimeters, and this side 4 centimeters. So if they're both rectangles, they will be similar because their sides are in proportion, and of course all rectangles have 4 90-degree angles. So what will the area be now? Well, I can just write 10 as 5 times 2 and 4 as 2 by 2. So the area of this shape will be 10, which I can write like this, times 4. So what we have here, it's the original area of 5 times 2, but we're timesing it by 2 squared. So it's 5 by 2, the area of the first shape, times 10 squared. So what I'm saying here is I'm writing it in this long way. We all know the answer is 40, but I'm writing it in this long way to show that when I double the length of each side, then the area doesn't double, it actually quadruples. I times it by 2 squared. So let's look at what happens if I triple the length of each side. Well, this side here will become 5 times 3, or 15 centimeters, and then the other side will be 2 times 3, or 6 centimeters. So when I multiply the areas together, what I have is 5 times 2 times 3 times 3. I have my original area of 10, and I'm multiplying it by 3 squared. So remember, 3 is the scale factor here. That's what I've multiplied each side by. So hopefully we're seeing a pattern. So whatever we multiply by each side, whatever the scale factor of the sides is, the area is multiplied by that squared. So if I multiply each side of a 2D shape by k to get a similar figure, the area will be multiplied by k squared. So as we saw in the first one, if you double the length of each side, the area is multiplied by 2 squared, or 4. The area is quadrupled. If you multiply each side by 3, the area gets multiplied by 3 squared, or 9. This will work for any number. If I halve the length of each side, the area would be multiplied by a half squared, which is a quarter. So if I half the length of each side, the area of the similar shape is 1/4 of the area of the original. So that's our rule for area scale factors. So note, when I say scale factor just by itself, I'm talking about the proportion of sides. Area scale factor is the proportion of areas in similar objects. So let's now use this to find unknown quantities. Okay, we're going to find the value of x and y in these diagrams. So let's look at the first two parallelograms. I'm telling you that they're similar. Of course, this area and volume scale factor only work for similar shapes. So we know that the scale factor is 10 over 4. Remember, I always said do larger shape divided by smaller shape. So that equals 2.5. That tells us that the sides of the larger shape are 2.5 times as long as the sides of the smaller shape. So if the scale factor is 2.5, the area scale factor, which I'll call ASF, is 2.5 squared, which is 6.25. So that means that the area of the larger shape is 6.25 times the area of the smaller shape. So x will just be smaller shape. Now when you're going from smaller to larger, you times. So 10 times 6.25, which just gives us 62.5 meters squared. How easy is that? So now let's look at the second pair of shapes, some sort of pentagon, and we're going to find y. So this time we're given both areas, and the thing we're trying to find is one of the side lengths. So we know that the area scale factor is, now remember we always do larger divided by smaller, so it's 30 over 15, which is 2. So that means the area of the larger shape is double the area of the smaller shape. From that, we can recover the scale factor. The scale factor is just going to be the square root of that, because the area scale factor is the scale factor squared. So that means that the sides in the larger shape are root 2, or like 1.41, times the sides of the smaller shape. So we can recover y really easily. Remember, because we did larger divided by smaller, we use the rule, if you're going from the larger shape to the smaller shape, you divide by the scale factor. So y will just be 3 divided by the scale factor, which gives us approximately 2.12, and it will be in centimeters. How easy is that? Let's now go and look at volume scale factors. So on your screen, we have 3 poorly drawn cubes. So let's look at this cube here. I'm going to give it a side length of 6 meters. We're going to look at what happens to the volume now that I've doubled the length of each side. So returning to our original cube here, its volume is just 3 cubed, or 27 meters cubed. So the volume of the larger cube, this one here, this will be 6 cubed, and 6 cubed is 216 meters cubed. So when I multiplied the length of each side by 2, I didn't double the volume. How much have I increased it by? Well, 216 over 27 is 8. I've actually multiplied the volume by 8. And the astute of you probably realize 8 is 2 cubed. So if I multiplied the length of each side by 2, then the volume increased by a factor of 2 cubed, which is 8. So let's look at the smaller one now. So I'm going to give it a side length of 1.5 meters. So that means each side has been halved from the original cube. So finding the volume of this shape here, it's just 1.5 cubed, which gives me 3.375 meters cubed. So the original volume was 27, and the new volume is 3.375. So once again, the volume scale factor is 8. So that means that this shape here has a volume that is 1/8 of this shape here. And that makes sense, because what I did was halve the length of each side, and a half cubed is 1/8. So I've just figured out, when you halve the length of each side of a 3D shape, then its volume is divided by 8. Its volume is 1/8 of the original volume. And that leads to our predictable rule here. So once again, when I say just scale factor, I mean the proportion that the sides are in. So if the scale factor is k, we found the area scale factor was k squared. The volume scale factor happens to be k cubed. So whatever you multiply by the length of each side, you cube that, and that's how many times the new volume will be. So if I were to multiply each side of a 3D shape by 4, the volume would increase by a factor of 4 cubed, which is 64. The volume would be 64 times as large as the original. So once again, we're going to use this to find some unknown quantities. So we're going to calculate the values of alpha and beta. So let's look first at the first 2 cylinders. What happened to go from this cylinder to this cylinder over here? Well, you can see we've multiplied the dimension, the radius, by 1.5. So the scale factor is 1.5. Now the volume scale factor will just be 1.5 cubed, which is 3.375. So that means that the volume of this shape here will be 3.375 times the volume of this one here. So very simply, alpha is just going to be 8 times 3.375, which is 27 meters cubed. So that will be the volume of that big cylinder. So now let's look at the small cylinder. So what have I done to go from here to here? Well, now I'm told the volume of each, so I can find the volume scale factor. So once again, we do larger divided by smaller. So it's 8 divided by 4.096. So putting that in our calculator, we get like 1.953125. So what that means is that the scale factor will actually be the cubed root of that. Because you're saying, what number do I cube times by itself 3 times to get 1.953125? So if you put that in your calculator, you just get 1.25. So that means that the normal scale factor from this one to this one is 1.25. Or in other words, this dimension here, the sides in this cylinder here, are 1.25 the sides in that cylinder there. So once again, we're going from a larger shape to a smaller shape. We divide by the scale factor. So beta will just be 1 divided by the scale factor, meaning it will be 0.8 meters. And there we have it. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.